Okay, good afternoon to all students. This is the first training for Singapore Junior Chemistry Olympiad 2023. So for the first training, we'll be doing separation and purification. So this topic really is all about selecting apparatus, planning how you would separate a mixture depending on what the mixture is. So we will go through the different types of apparatus. We will go through how do you collect gases, how do you dry gases, which should hopefully be a revision of Sec 3 work for all of you here. All right. So first, we have various apparatus for measuring different quantities in the labs. In particular, to measure volumes of liquids and solutions, there are various options, right? So you can see there are three different apparatus that can be used to measure volumes of liquids and solutions: measuring cylinder, burette, pipette. Now, what's the difference? Measuring cylinder is used to measure approximate volumes of liquids and solutions. So take, for example, you wanted to measure 250 cm3. You would use measuring cylinders to do that, okay? Burettes and pipettes. So you have seen this in the lab. Burettes come with multiple markings and a tab at the bottom that you can turn to open it or close it. Burettes are used to measure accurately the volumes of liquids and solutions. So for example, if you wanted to measure 25.10 cm3 of hydrochloric acid, 25.10 is an accurate reading, you need to use a burette. All right. So burettes, you need to know the precision is up to 2 decimal places. So burette readings, we quote it to 2 dp. Then we have the pipette. Now pipettes are unique because there is only one marking. So unlike the burette, pipettes only have one marking. And as a result of that, they are used for measuring out a fixed volume of a liquid or solution. And for our lab, usually the pipettes come in 25.0 cm3. This means that in the lab, the pipettes that we have can only measure 25.0 cm3 only. And take note, this is 1 dp. All right. Now, so do pipettes only come in 1 dp and do pipettes only come in 25.0 cm3? The answer is no. There are smaller pipettes available. So for example, if you work in a biomedical science lab in future, you will use what we call a micro pipette. Okay, so besides pipettes, there are micro pipettes. And as the name suggests, you can imagine micro pipettes measure relatively smaller volumes. All right, micro pipettes can measure 1,000 microliters. 1,000 microliter is basically 1 milliliter. All right. Now, why such a small volume? Usually in biology experiments, especially experiments involving cells, enzymes, you cannot be using so much solution and liquid. It's a waste of the liquid, right? You don't have many cells to begin with. So why do you need so much solution to put your cells into? Don't need. So usually for bio experiments, we use micro pipettes. And micro pipettes usually come in the 1,000 microliter. Okay, 1,000 microliter is equals to 1 milliliter. Okay. Now that's for liquids and solutions. Now let's talk about gases. Now gases are important. All right. We need to be able to measure volumes of gases. And the way to do that is a gas syringe. All right. Now, this is commonly needed in speed of reaction experiments. Now, this is important for you to know. Okay. So very often, if you were to look at your 10-year series, or if you were to look at the Chemistry Olympiad sample questions, they will actually ask you to suggest apparatus to measure the speed of a chemical reaction, right? If the chemical reaction produces a gas, then a good way to measure its speed is to measure the volume of gas given off. And how would you measure volume of gas? Gas syringe. All right. Now, whenever you use a gas syringe, there's one source of error, or rather, should I say there's one assumption. Okay. There's always one assumption when you use a gas syringe to measure volume of gas. So how a gas syringe works is basically the gas enters the syringe and the gas pushes the plunger outwards. So we are assuming that there is actually no friction between the gas syringe and the plunger. All right. We have assumed that the volume readings are accurate because there's no friction between the gas syringe and the plunger. Now, how is this even important? Now, this is important because if there is friction between the gas syringe and the plunger will not move outwards uniformly. It will not move outwards smoothly. As a result of that, your volume reading for the gas will be less accurate. Okay? So how do we try to minimize this friction? This is the reason why for gas syringes, usually we will try to ensure that there are no rough surfaces on the gas syringe. We will try to ensure that we maintain it such that the surface is smooth. Okay? Ken? Okay, that's it for the gas syringe. Moving on, I think the next few apparatus should be no stranger to you. The electronic mass balance is used to measure masses. All right. Now, when do you need to measure mass? When it's a thermal decomposition experiment. Okay. So for the SJChO, what is decomposition? So I can show you an example. So take, for example, you have a compound like calcium carbonate. Calcium carbonate can decompose when heated to form calcium oxide and carbon dioxide gas. So importantly, because it breaks up, decomposition is to break things up. So you have broken one big compound, calcium carbonate is one big compound, up into two smaller substances, of which one of them, CO2, is a gas. Therefore, it will escape. Right? Gases will just escape. So the mass of the solid left. The mass of the solid left will decrease because some of the mass is in CO2. The CO2 has escaped. All right. And that's why the mass of the solid decreases. So very often to measure the speed of this reaction, we would also use an electronic mass balance because it's a thermal decomposition experiment. Okay. Ken? So for the SJChO, don't worry, we will get on to writing equations in one of the training sessions as well, right? But just to let you know what is a thermal decomposition for now. A thermal decomposition is when one big substance, one big compound breaks down into smaller substances by heating. Okay, so carbonates can decompose. Nitrates and sulfates can also decompose, as you would learn later on. All right. Okay. So the next two, easy, right? Thermometer used to measure temperature. Temperature is usually needed in energy changes experiment. For example, you want to find out if a reaction is exothermic or endothermic. Now, a quick introduction. Exo. X means external, outwards, meaning heat energy is released to the surroundings. Okay, so exo means outwards, external. So heat energy travels, transferred outwards to the surroundings. Now, this is important. If heat energy is released, the temperature increases. So one good example is burning, right? When you burn something, heat energy is released. This tells you that burning is an exothermic reaction. Okay? So the opposite of that is endo. Okay, so the pure bio students should know this very well because when you learn cells, you learn endoplasmic reticulum. So the word endo means inside. Okay, so you can imagine endothermic means heat energy is taken in or absorbed. Okay, means the same thing, taken in or absorbed from the surroundings. All right, so the temperature decreases, it becomes colder. All right, so that's an introduction to exothermic, endothermic reactions. Okay, exothermic, heat energy is released, so the temperature becomes hotter. Endothermic, heat energy is taken in, so temperature decreases, becomes colder. And to find out whether it's exo or endo, you need to use a thermometer to measure the temperature change. Okay, finally, stopwatch. Stopwatch is measure time, all right? So obviously you need time when you talk about speed, okay? Ken? So this is just a quick revision, Okay, moving on, we have the familiar 3 methods to collect gases. Please don't forget this. Okay, even if it's not tested for ChemO, it's still important later on when you do your planning for practicals. Okay? Now, the 3 methods to collect gases, I won't harp too long on it. There are 3 methods: displacement of water, upward delivery, downward delivery. So displacement of water basically involves bubbling the gas into water. And then you collect it in a gas jar that's inverted into water. So you can see bubble, bubble. You can see bubbles, 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 bubbles. So in order to collect these gases, the gas has to be insoluble in water. Why? Imagine if the gas dissolves in water, then you will not even have any more bubbles coming out. The bubbles of gas will just dissolve immediately. All right. So you must ensure that the gases collected by displacement of water are insoluble in water. So what gases are these? Well, it's actually easier to learn which gases are soluble. Okay. So which categories of gases are soluble? Acidic, alkaline gases are soluble in water. So for example, SO2 soluble in water, NH3 ammonia soluble in water. All right. So because they are soluble, they cannot be collected by displacement of water method. Okay. Next, we have upward and downward delivery. So upward, as the name suggests, the gas floats upwards. Floats upwards means less dense, lower density than air. Okay. Downward delivery is when it's more dense than air. That's why it sinks. Okay. Ken? So these are the 3 methods for gas collection, which I'm sure we have studied. Okay, let's move on. Now, besides collection of gas, you must also learn how to dry gases. So we usually use different drying agents. There are 3 drying agents you need to know: concentrated sulfuric acid, calcium oxide, as well as fused calcium chloride. Okay, now concentrated acid can be used to dry gases. However, it's an acid. So because it's an acid, it cannot be used to dry alkaline gases. Okay, so you might have remembered from Sec 2 and 3, acids react with alkalis. That's neutralization, right? So you cannot use concentrated acid to dry an alkaline gas. It wouldn't work, because the gas would have reacted with the acid. It wouldn't have just been dry. It would have reacted chemically. You don't want that to happen. You want the gas, okay? So it cannot be used to dry alkaline gases. So what is an example of alkaline gas? Ammonia. Ammonia is an alkaline gas, all right? Next, calcium oxide. Now, calcium oxide is alkaline, it's a base. So it cannot be used to dry acidic gases. Okay. Now, for now, you may not know which gases are acidic. That's fine. We'll get to that in a while, maybe in another training session. Okay, so calcium oxide is also known as quicklime. That's the common name for that. Okay. In fact, just a fun fact. Okay, whenever we say lime, slick lime, quick lime, lime water, it's not related to the fruit lime. It's not related to the fruit, okay? When we say lime in chemistry, very often we are referring to a calcium compound. So the Sec 4 students, you should have heard a lot of these names already. Quicklime, slaked lime, lime water, limestone. If you think about it, actually all these substances contain calcium in it, okay? Just a fun fact. All right, finally, we have fused calcium chloride. Now, fused calcium chloride has a different name. Sometimes it's also known as anhydrous calcium chloride. Okay, but it means the same thing, all right? Anhydrous and fused calcium chloride just means dry calcium chloride. So because the calcium chloride is very dry, it can actually suck up and absorb the water from the gas. Now, fused calcium chloride is very useful because it can be used to dry most gases. Most. All right. Now, it can be used to dry most gases except fluorine gas. Okay, except fluorine. So it cannot be used to dry fluorine gas. So hopefully the SJChO students, you can think about why that is the case. How come F2 cannot be dried using CaCl2? Okay, hopefully you know the answer to that. Okay, for the SJChO students, don't worry, we have a training session for another topic on this. Okay, so that's it for drying, collection of gases. That's it for selecting apparatus. So such questions may come out in the chemistry Olympiad. Okay, now let's move on. Now, the next part should also be very familiar to all of us. So both the SJC3s and the SJC4s have done this topic on separation techniques. Okay, so the first technique is filtration, which I'm sure all of us, we are familiar with. So filtration is used to separate insoluble solids from a solution. All right, so take for example, separating sand from water, separating sand from salt solution. Okay, so how does filtration actually work? Filtration works because the solid is too big to pass through the pores of the filter paper. So your filter paper contains holes. These holes are called pores. So the size of the pores determines its filtration efficiency, right? If the pores are too big, then everything passes through it. So obviously the filter paper pore size must be limited so that it can trap insoluble solid particles. Okay, so the solid that remains on the filter paper is called the residue, and that's your insoluble solid. The liquid that flows through the filter paper is called the filtrate. Okay, now this is the standard apparatus and setup that we use to filter an insoluble solid out from a mixture. However, if you go to a research lab, very often you wouldn't just use filter paper and filter funnel. Very often you will see apparatus that looks like this. This is called a Büchner filtration apparatus. It looks kind of similar, right? There are some similar parts. For example, you still have a filter paper. For example, you still have a filter funnel, but right now it's called a Büchner funnel. Okay? So these parts are similar to what you have learned for filtration. However, there are some interesting new parts to it. What are the new parts? Firstly, there's a rubber bung on the flask. Secondly, there is suction so that you create a partial vacuum in the flask. So this is a bit like combining your filtration setup with a vacuum cleaner. A vacuum cleaner is able to suck up dust and dirt because there's a vacuum, right? A vacuum basically is empty space, no particles. So inside your vacuum cleaner, there's a pump that sucks out the air so that at least that space is empty. There's no air in it. So how would a vacuum be useful in filtration? So it's similar to a vacuum cleaner. It's sucking things out. So what do you think the vacuum is sucking up? Is the vacuum sucking up your insoluble solid, or is the vacuum sucking up the filtrates? Okay, so if you think about it, the solid cannot pass through the filter paper. So definitely the vacuum is sucking up whatever is in the flask. So the vacuum sucks up the air in the flask. Okay, and let's relate this to physics. If you suck out the air, the pressure in the flask is lower. When there is less air, there will be less air pressure as well in the flask. Okay, so how is this even useful? Okay, well, if you think about it, when the pressure is lower, this means that the filtration is faster. Why is it faster? Because then your filtrate will flow through the filter paper more quickly. The filtrate is effectively sucked down into the flask. Because the air has been sucked out, the filtrate is now sucked into the flask to replace the space occupied by the air. So this is commonly used in a research lab to speed up the filtration process. Okay, we need to do this very often because we cannot afford to wait like 3 hours in order to filter, say, 500 ml of a mixture. If you do 500 ml in our school lab, you may need 3 hours because the liquid, the filtrate flows through very, very slowly. All right. So a Buchner funnel and a Buchner filtration apparatus allows you to speed up this process. You could reasonably filter 500 ml of a mixture within, say, 15 minutes. All right. So it's a bit like a vacuum cleaner, right? Imagine if you were to sweep the floor, wow, it takes forever to sweep out all the dust, right? But a vacuum cleaner just speeds up the entire process of sucking up the dust. Okay. You will commonly see this in chemistry labs as well as biomedical science labs. Okay. All right. Now, besides this, what are other applications of filtration? A good application of filtration is actually your mask. The mask that you use to wear, right? Okay, contains pores that prevent bacteria and viruses, okay, from exiting and entering the mask. Okay, so this is actually called microfiltration. Okay, so typically, your masks are microfiltration. What that means is that the pore size, the holes, how big are the holes? The pore size is in the micrometer range. Okay, so what is micrometer? Okay, physics students, hopefully we know our prefixes are 1 micrometer is 10 to the power of -6 meters. So your mask, typically your mask is in the micrometer range. It can filter away particles that are about 1 micrometer in size. Okay, then we move on further. Some of the masks and some of the membranes can do ultrafiltration. Okay, so we have some pure bio students here. So one of the topics in pure bio that you have learned for the Sec 4s is excretion, where you learned about the function of the kidney and the tubules in the kidney, right? So your kidneys actually filter urine, all right? They filter urine such that proteins in your urine don't get excreted from the body. How does your kidney do that? Your kidney does that by having a membrane that is capable of doing ultrafiltration. So the pore size is about 0.1 micrometers, 20 nanometers. So nanometers is even smaller. 1 nanometer is 10 to the power of -9 meters. So your kidneys are able to filter out particles, okay, that are about 10 to the power of -9 meters. And that's the amazing part of the human body, right? And that's why we study bio, right? Okay, so that's ultrafiltration. It's present in your kidneys. Okay, and so on and so forth. Okay, NF stands for nanofiltration. So nanofiltration filters out particles that are about 1 nanometers. Finally, the last one, reverse osmosis. Now, reverse osmosis is one of the important processes for Singapore because reverse osmosis is how we purify water. So you might have heard reverse osmosis very often, probably in lower sec you learn under geography, right? One of the 4 national tabs right now is reverse osmosis, which is new water. How does it work? Reverse osmosis works because the membrane has such a small pore size that it can actually filter out salt. Then you'll be like, huh? But isn't salt soluble in water? Yeah, salt is soluble in water. But the membrane is so small in pore size that it can even filter out the sodium ions and the chloride ions. This pore size is so small that it can even filter out ions, you know. And that is how reverse osmosis works. You are basically filtering out all the ions in the water. So you can convert dirty water into clean drinking water, which is what we call new water. Okay? Now, why do I spend so long going through this? It's because the Chemistry Olympiad will not just test you on the basic filtration. You need to know extensions like Buchner filtration, microfiltration, ultrafiltration, nanofiltration. You need to be relatively familiar with what you learn in physics, like prefixes, micro, nano. What does it mean? Okay. Now, moving on, The next two should be very, very familiar. Evaporation to dryness and crystallization. Okay, I believe both are not strangers to you. Let's just go straight to crystallization. Now, crystallization follows a fixed set of steps. First, you will heat the solution until it's saturated. Then you allow the solution to cool and crystallize. And then you filter to collect the crystals, wash it with distilled water, and dry the crystals between pieces of filter paper. So I believe you might have done this in lower sec, you might have done this in sec 3 as well. Okay, so that's how you obtain crystals from a solution. Okay, that's what your teachers must have taught you. But now let's focus on this word, saturated. What does saturated really mean? So let's go to the graph at the bottom. Okay, and you will see this in your MCQs if you look at other schools' pure chem MCQ papers. This is what we call a solubility curve. Immediately you see something important. Solubility refers to the mass of the compound that can dissolve in a fixed volume of water. So if you notice, right, the solubility changes with temperature. So it's quite clear for P, the solubility increases as temperature increases. Okay? P is a typical salt, like copper 2 nitrate, copper 2 sulfate. So these common salts will just follow graph P, where solubility increases as temperature increases. How is this even important? Well, that is how crystallization works. Let's say if I heated my solution up to 80 degrees Celsius. Okay? And at 80 degrees Celsius, the solubility, let's say, is 200. 200 grams can dissolve in 100 cm cube of water. This is where it's saturated. This is the saturation point for 80 degrees. So what does saturated mean? It means you have the maximum mass of salt dissolved. Saturation means cannot dissolve any more salt. It's already reached the maximum. It can't dissolve more than 200 grams already. So when it's saturated, it means it has hit the maximum mass of salt. That's called saturation point or saturated. Okay? So this is crystallization, right? So the first step is heat till it's saturated, right? What's step 2? Let's read step 2. Allow the solution to cool. Cool means what? The temperature go down. Room temperature is about 30 degrees nowadays, are hot, right? So maybe 30 degrees is here. So now let's look. Maybe at 30 degrees, only 80 grams of the salt can dissolve. So what on earth has happened to this difference? What on earth has happened to the 120 grams of the salt? 120 grams of the salt, P, has to crystallize out as solid crystals. So that's how crystallization works. You are making use of the fact that solubility is lower when it's cold, higher when it's hot. So when you cool things down, the solubility decreases, and as a result, it has to crystallize out. So in this case, 120 grams of the salt will crystallize out. Okay? So make sure you know how to deduce, oh, it's 120 grams. Okay, so in the test, if we give you this graph and with numbers, you should be able to work out what's the mass of the salt that has crystallized out. Okay, so this is actually a common pure chem MCQ question for this chapter. And I'm not referring to Chem O, I'm referring to pure chem, like end of year exam, prelims. Okay, so for my Sec 4 students, if you have done my MCQ revision set for salts, you will realize that this question comes out once or twice in that series of questions. Okay? Now, salt P is able to crystallize out because you can see that the solubility really increases with temperature. Now, if you look at salt R now, it's a different story. Salt R solubility does not change with temperature. And because the solubility doesn't change with temperature, it is not possible to crystallize. Okay, so what is an example of this salt? How come this salt so special? This salt cannot crystallize. A good example is sodium chloride, which is a salt that you commonly eat. Sodium chloride solubility doesn't really change with temperature. And as a result, it's not really possible to crystallize. Now, besides sodium chloride, what other salts demonstrate this? Insoluble salts as well. So my pure chem students, you should know barium sulfate is insoluble, so it will also be impossible to crystallize. Okay. All right. Moving on. Okay, let's just copy down first, in case you need more time to copy. The next one is on distillation, which I think should be familiar to all of you now. Okay, I'm just going to move on to distillation quickly. So there are two types of distillation, simple distillation and fractional distillation. You can tell the difference by looking at the apparatus. Fractional distillation needs to have a fractionating column. All right. The fractionating column has glass beads inside. That increases the surface area for the vapor to condense. All right. Now, fractional distillation is very important because it can be used to separate two or more miscible liquids with different boiling points. This is crucial. So what's the meaning of miscible? Miscible means it can be mixed together. It will mix together to form one homogeneous layer. And that's why we don't separate oil and water using fractional distillation. Oil and water are immiscible. And because they are immiscible, we use the separating funnel to separate them. Okay, so oil floats on water, so you just need to use a separating funnel. They are immiscible. So when do we use fractional distillation? Whenever we want to separate two or more miscible liquids and they must have different boiling points. This is crucial. All right. So when do we use it? We use it for air, separate gases in air. So air contains nitrogen, oxygen, argon. That's how we separate gases in air. We can also separate the components of crude oil. So in one of the training sessions, we will do introduction to organic chem. So under the introduction to organic chem, we will bring you through how we separate crude oil into various organic compounds. And the method is fractional distillation. Okay. Now let's move straight to the questions. So this was taken from my MCQ revision set. Yes. Okay. Yup. Okay. So the setup shown is used to purify a sample of butanoic acid. Boiling point is 164 from water. Water's boiling point is 100. So immediately you can tell, right? Who will boil first? Water boils first. Between the two, water boils first because it has a lower boiling point. So now they want you to say which graph shows the change in concentration of butanoic acid. Concentrated versus dilute. So think lah, if water boils first, that means there's less water left in F because the water is boiled off. If there's less water left, it becomes more concentrated. Concentration increases. This is like coffee, right? If you make coffee with less water, then it's more concentrated coffee. So quite obviously, the answer for this is B. The concentration of butanoic acid should increase. And the main reason is because water has boiled off first. Now let's look at the next question, which is also from my MCQ revision set. Okay, let's move on to the next page. So the next page is also fractional distillation, but now we are separating ethanol and water. Ethanol's boiling point is 78. Water is 100. Clearly, 78 is lower than 100, right? So just now, water boiled first. In this question too, ethanol boils first. Because ethanol has a lower boiling point. And as a result of this, because it boils off first, there's less ethanol left. There is less ethanol left in the flask. Okay? So just now was less water left. That's why it becomes more and more concentrated, right? Because water dissolves stuff. Water is a solvent. Now it's different, right? Now there's less and less ethanol left. So what happens to the concentration of ethanol? It's like saying you use less and less coffee powder. Less and less ethanol dissolve means concentration decreases, less and less concentrated. So the answer is A. Okay? So these are the kinds of possible MCQs you could see for fractional distillation, okay? Quite commonly seen in other schools' papers, okay? And we have saved the best for last, which is chromatography. Okay, so I believe all of us are familiar with chromatography. We are now on page 9 of the notes. Okay, this should serve as a revision for all of us here, especially the Sec 4s. If you have forgotten chromatography, you need to learn chromatography again because you will need it for your planning very, very soon. Okay, so how do we do chromatography? This is the setup on page 9. Okay, I hope you remember all these things, including the 3 questions on page 9. Why must the solvent be below the pencil line? Why must the pencil line be drawn using a pencil? Why must the flask for the chromatogram be covered? I hope you still remember these things. And I hope you remember chromatography separates substances based on their solubilities in the solvent. The fact that your food colorings, your paints, your dyes, your drugs in the urine can be separated is because they have a different solubility in the solvent that you had chosen. Okay? Okay, so moving on to page 10 quickly. How do we interpret chromatograms? I hope you remember this. When you see only one spot on the chromatogram, that means the substance is pure. If it remains on the start line, that means the substance, that particular dye, is insoluble in the solvent that you had used. Okay? So all these things, I hope you remember. And for pure chemistry, you learn something extra, which is something called RF value. Right? RF stands for retention factor. So how do you calculate the RF value for a particular spot? You must take the distance traveled by the spot. Okay? So in this case, the distance traveled is X. Okay, I think the labeling is not very clear. Okay, X is the distance traveled by the spot. Y is the distance traveled by the solvent. So X over Y gives you the RF value. Oh, sorry. Okay, I think there's a shift in the text boxes. So can you please correct the diagram? Make sure you get the correct diagram. So X over Y. Can you please relabel the diagram on page 10? All right. Okay, so this is actually a ratio. It's a ratio of the distance traveled by the substance, the spot, to the distance traveled by the solvent. Okay? So you need to be careful when calculating RF value. Okay, so my Sec 4 students, you must remember last year's Pure Chem WA1. The start line may not be at 0, right? The start line could be at 2 cm. Then this one could be at 12 cm. So the total distance traveled by the solvent is only 10 cm, okay? So in this case, Y is equals to 10 cm. All right, so don't always assume the start line is 0. It may not be 0. All right. All right, let's move on to the second last page, page 11. I think we're doing good on time. Now, RF value is really important because RF value allows you to actually identify what the substance is. So it's not just about separating a mixture anymore. It's about analyzing and identifying, oh, this is this banned drug. Oh, that is heroin. That is methamphetamine, for example. All right. How do you do that? Now, if chromatography is done properly, the RF value allows you to actually identify the substance because there is actually a dictionary of RF values of known substances in different solvent mixtures. So take, for example, if I were to analyze urine for banned drugs, right? I can actually look up the RF value of banned drugs in, say, a solvent mixture of ethanol and water. There is actually such a dictionary. You can just Google and search for it, okay? So if you do more chemistry lab work in future, you would actually make use of this dictionary encyclopedia of RF values. And it's very useful. Okay, finally, let's go do this question now. This is actually from other schools' prelim papers. This is what we call two-dimensional chromatography. So you do chromatography once in this direction first. And then you rotate clockwise 90 degrees. So you must visualize, okay? So visualize what? When you rotate clockwise 90 degrees, the new start line is here. So when you rotate 90 degrees, the new start line is what I've drawn in green, okay? So what do you see? If you rotate it, this dye has formed two spots. This dye remains on the start line. This dye, the last one, remains on the start line plus one more spot somewhere further away. So you have to count how many spots are there. 1, 2, 3, 4, 5. Right? How come I don't count the last spot? This one has moved up, right? It's no longer on the start line. It has completely moved up. Okay, so if you count properly, there are 5 spots, 5 different types of food colorings. Now, this is called two-dimensional chromatography because what you do is do chromatography in one direction first, flip it 90 degrees, do in another direction. Now, you do 2D chromatography, two-dimensional chromatography, to improve separation of substances with similar solubilities. So sometimes your substances can have similar solubilities. That's why the spot seems to merge together. That's no good because you wouldn't be able to achieve good separation. To improve the separation, you will need to use 2D chromatography. All right. All right, so that is two-dimensional chromatography. Let's go to the last page, which I hope my students and the SJChO Pure Chem students will recognize. The last page is on circular radial chromatography. Okay, so there are many types of chromatography. There's ascending method, descending method, which you have seen in your homework last year. Okay, and for the SJChO Pure Chem students this year as well, because the assignment that you got is quite similar to what I said last year for the 4E Pure. Okay. Now let's go on to the circular chromatography. Now this one has another name. It's called radial chromatography. Radial means radius, or radius of a circle, right? Now basically it's very simple. Just take a piece of chromatography paper that's circular, put one drop in the center, then put one drop of solvent and let it separate. it will separate into concentric circles. You need to know the rule is the same. The more soluble the substance, the further it will travel together with the solvent level. Okay? So how do you calculate RF? That's the question, right? So the solvent level is here. Let me draw for you. The solvent level is here. Pointed out to you in the arrow. This is the solvent level, right? Solvent level or solvent front. So how do you calculate the distance traveled by the solvent? It's a circle. In a circle, the best distance to measure is the radius. Radius from the center to this. So this is y. Y is the distance traveled by the solvent. Then how do I calculate RF value of the purple color dye? Measure the radius. So the RF value is still x over y. Okay, so that's how you calculate the RF value using a radial chromatography. Now, how do you translate this back into the usual standard chromatography? Well, something difficult, right? First, we have the purple color. Then, oh, sorry, first you have the yellow color, right? Yellow color. There's yellow color, I forgot. There's the yellow color. Then you got purple color. Okay, then after that, you have the blue color. The blue color is the most soluble. Finally, the black color represents your solvent front. Okay, so it's the same method, same technique, same principle, just that you've done it on different kinds of chromatography paper. Okay. Finally, how can you prove that a substance is pure? So I think all of us know this. The best way and the most confirmatory test, the best way to confirm that something is pure is its melting and boiling point. So please measure its melting and boiling point. Make sure it's fixed melting and boiling point, okay? Thank you. All right, so let's do a sample question now. If you look at the sample question from the Chemistry Olympiad, to prove a colorless liquid is pure water, keyword here is pure, which measurement is the most reliable? So based on what Mr. So has told you, to test out the purity of water, we should always look at the BP, MP, so boiling point. All right, so the answer is C. Okay, A, B, and D wouldn't be accurate. All right, it's not the most reliable. All right, so you can see even the SJChO is not so hard, so long as you can handle this. Okay, finally, before we go, I have 5 minutes, right? Now, last year, they also asked some interesting questions. So for example, okay, we can go back to distillation. We can go back to simple distillation. Okay, this is on page 6. Simple distillation is used to obtain pure liquid solvent, right? So for example, you obtain pure water from seawater. Now, the process, the water obtained here is called distilled water. So distilled water obviously is obtained by simple distillation. But you see in the lab, there's also another word called deionized water. If you go to the lab, you see the water bottles, right? It's labeled deionized water. Okay? Hi. All right, so deionized water, how is it made? Is it made using simple distillation as well? Typically, no. If it's deionized water, right, it actually means it's made, deionized. If it's deionized, it means it's made using ion exchange chromatography, which is not in the O-level syllabus. So what happens is that you pass it through a membrane that filters away ions. All right, so like just now, reverse osmosis, similar. So ion exchange chromatography basically filters away and separates out the ions from water. So deionized water is typically made using ion exchange chromatography. Having said that, Actually, deionized water and distilled water are the same thing, right? They are pure water without any ions, without any dissolved substances. Okay, so both of them are the same thing, it's just that they are made using different methods, hence they are given slightly different names. So this was asked last year during, I think, round 2 of the chemistry Olympiad, which I think one of you here took part in. Okay, so that concludes our lesson for today on separation and purification. The next lesson will be next Wednesday at the same time, 5 o'clock, same Zoom link. We will be doing atomic structure and ionic bonding. So I shall stop the recording here.